You're going for Diwali holidays.
Uh, no such plan as of now.
Maybe we can see a lot of bags packed in the background.
Ah, okay. These are actually empty. They are only bags. That's all.
Okay.
So let us start today's session. So I plan to briefly discuss about the digital precoding, or to be precise, fully digital precoding and analog precoding, and what are the appropriate situations for them to use. So in the course we are hearing those two terms repeatedly again and again, that is FR1 and FR2. Can one of you please point out what actually this point to, when I say my system is operating in FR1 or mine operating in FR2, what do I exactly mean by that?
So FR1 is below 6 gigahertz frequency.
Okay, so FR1 is sub 6 gigahertz, and when it comes to FR2,
So FR2 we call it as millimeter wave. So it will from 24 gig to I think 51 gig.
okay, so I can roughly can say 24 to 52 gigahertz. Okay, and these frequencies we are talking about carrier frequency, right?
Right.
And so when I'm operating in FR1 and FR2, apart from this carrier frequency, is there any change in bandwidth of the system? Like as of now, we talked about 5G NR standard bandwidth is 100 megahertz. So does that equally applicable for FR1 and FR2?
So for FR1 it is 100 megahertz. For FR2 it is 400 megahertz.
So here I have 100 megahertz, and here I am having 400 megahertz. Okay. So FR1 I have a carrier frequency below 6 gigahertz and a bandwidth of 100 megahertz max. So bandwidth kind of is constant, but still I need to serve lot of users. So what is the main constant when it comes to FR1 system design? What is the constant here? For example, I can point out few good things. For example, my channel is uh, good in this regime, so that is pro. So what about the con here for FR1? Like, what is the problem? Is there some resource constraint? So the issue is we cannot go beyond that 100 megahertz. So bandwidth is the main constraint here. So we have already seen the use of MIMO technology. So when I'm saying that bandwidth is the main constraint for FR1 system design, how having multiple antennas at transmitter and receiver side can solve the problem?
By sending data in parallel streams.
Okay, so have to send parallel streams. So you are going to use your multiple antenna at both transmitter and receiver side to send multiple layers to improve the overall spectral efficiency. Fine, that is about FR1. So in FR2, when we move, good part is that now we have bandwidth 400 megahertz. So what is the issue with FR2 then? We have so much bandwidth. Is there any problem that arises in FR2?
The coverage footprint will be low because we are operating at very high frequency.
Okay, coverage footprint is low, and it is low because we are transmitting at higher frequency.
Right.
So you are saying that the path loss we are going to see is much more for
Much higher. Correct.
for same distance in FR2. Okay, so does we use the MIMO principle here to send parallel layers for FR2 also to solve the issue?
Yeah, we can use that also.
Okay, we can theoretically, but the issue is for FR1, why are we sending parallel streams in the first place? Can you remind me once? For FR1, what is the purpose of sending parallel streams?
To increase the SNR and improve the throughput.
Okay, so basically, I have limited bandwidth, so I have to send multiple layers at a time to compensate for that, to achieve higher and higher data rate at a limited bandwidth. But for FR2, I don't have such constraint. I have a very large bandwidth, so I can transmit a lot of data. So multi-layer transmission is not really required here. So when you say like coverage footprint is low, can we go into bit more details like how the channel characteristics changes in that regime? Let's see if we are operating on so high frequency. Let's talk about what about the signal penetrating a wall or something. What happens at this high frequency?
So as per my knowledge, the maximum the FR2 frequency can travel up to 200 or max to max 300 meter.
Okay, but that is given we have a line of sight path, right?
Correct. Without any yes.
So at this high frequency, your penetration power is very low. Whenever some kind of blockage comes into between, maybe a building, maybe a car, or a tree, or maybe our walls, if we pick. So the FR2 performance not only drops, it kind of become infeasible. So since we have higher frequency, uh, since we have higher bandwidth, we are not really concerned about parallel streams because the whole purpose of sending parallel streams because we have limited bandwidth and I have to multiplex multiple layers to increase the data rate. But here since my bandwidth is itself much large, so I can send a single stream and can get good what is that, very high data rate. So we can like one stream is sufficient. But the issue is you are saying the channel is the issue, so it need to be line of sight kind of. The moment there is no line of sight path, that entire system is supposed to break down. And also you mentioned that coverage footprint is low. So for FR1, if the base station transmits something, and if we at a certain distance we consider the receive signal power is quite good for a user, but the moment we keep the everything same, for example number of antenna at base station, the distance to user, but we move to FR2, that is sending with a carrier frequency of around 24 to 52 gigahertz, the signal power that I'm going to see at the user is much low. So my SNR is of course going to go down, and SNR goes down means your spectral efficiency is going to be bad only. So here we have the flexibility, or to be honest, it's not a flexibility, it's like a luxury to have a single stream. So I can live with single stream in FR2, but what you mentioned about the coverage footprint, that's the real issue. So is there any way I can what is that improve the signal power at user end by using MIMO? Because parallel streams is not the way to improve signal strength, right? It's merely about having multiple streams, we have separate SNR for them. But FR2 I am saying that I can live with single stream, no issue, but the issue is going to be my uh, signal to noise power ratio is very poor at some distance. So using multiple antennas at transmitter and receiver, is that going to help out in any way apart from sending parallel streams? Because sending parallel streams anyway is not going to make much sense here. I hope I am able to like present my case. The thing is my like SNR is going to be very low at a particular distance. So how we can solve this issue is using multiple antennas.
So by forming narrow beam with high gain, high beam formation gain.
Okay, so narrow powerful beams are my way out. And how these beams can be created, by the way?
By using appropriate precoder.
By using appropriate precoder. So basically I am going to use multiple antenna at transmitter side. Let's talk about this is multiple antenna transmitter, and this is multiple antenna at receiver end. So you are saying I am supposed to form a narrow beam of this kind, so the entire power is concentrated in this regime and nothing really is transmitted all other direction. Similarly at user end I have to form the receive beam forming another beam, because the transmit beam former may not be sufficient, because the, as you mentioned, the coverage footprint or the path, no, coverage footprint is so low, that is the same thing as saying path loss is very high. So basically you are trying to have the beam forming gain at both transmitter and receiver to compensate for that. Because actually if you look at the path loss expression, you can roughly say that it's proportional to gt times gr over some scalar times lambda square. Now lambda is the wavelength that is inversely proportional to our frequency. So FR2 high frequency means low lambda, so path loss decreases with lambda. To compensate for that, we are bringing in this GT and GR, where GT and GR are the beam forming gain at transmitter and receiver respectively. So that is how we are able to do that. So is there any difference in number of antennas that is usually used in FR1 and FR2? Let's talk about the transmit side first. At base station, anything you can think of? Like what is the let's say standard, or I will say usual number of antennas at the base station for FR1? 30 to 64, right? So FR1 is, let's say it's 30 to 64, like that. What about FR2? Would the same number of antenna suffice, or
Yes, yes.
okay,
More is better, but
more is
usual
better?
cases. Yeah.
So apart from all these uh, problems we are hearing about FR2, like when we are talking about transmit antennas, what is the like benefit of operating in the FR2 range in terms of antennas? For example, you are saying FR1, I told that it's 32 to 64. For FR2, you told the mode is better. So let's talk about maybe 120 to 256. But that is going to take a lot more space, right, compared to FR1, or is it not? Because in FR1 I'm putting 32, let's say 64 antennas, and FR2 let's say I'm putting 256 antennas. So that's four times increase. So that is also going make it a bulky kind of device, right? Like 256 antennas, or there is some catch here.
Yeah, it's a pre-coding is done in analog domain or RF domain.
Okay, that will come to that. That is about RF chain and all that. But as of now, if I keep the RF chain out of equation, let's even talk of antennas even. Let's say when you have a 64 antennas, I'm talking about FR1. So they are placed like this. Like for example, I'm considering the simplest of the module, that is uniform linear array. So they are basically aligned over a line, and this is FR1. So there are total 64, and FR2, I'm saying I have similar uniform linear array, but now I have 256 such antennas. So that is also going to take a huge space, right? So is the space that they are going to take in terms of antenna, are they comparable, or FR2 is higher because it's using higher number of antennas, or how is it?
The spacing depends upon wavelength, and wavelength is short in case of FR2.
True. So it's not about individual antenna size. Most of the antenna space is taken by the spacing. So we have to keep a minimum distance between them to avoid this correlation and mutual coupling kind of issues. So that is lambda over 2. So the moment I am moving from FR1 to FR2, there is a almost sorry, 1/10 decrease in the wavelength. So therefore, even if you are using 256 antennas, you can fit them in a compact way. Okay, this is about the transmit antenna. There is increase in number of antennas, but not much. What about at user end? Like for if we talk about the simple mobile in FR1 and FR2, if they are operating, what is the difference in number of antennas?
FR2 antennas are more.
Okay, and any range?
816 of that kind.
So at FR2, if we talk about users, it's like 4 to 8 or maybe 16 antennas even. Whereas in FR1, it's 1, 2 maybe, not more
4.
than that. So fine. So you are talking about that RF chain thing. So let's talk a bit more about. Uh, so this is about antenna. Antenna doesn't take much space at all. So you've seen. So what is the RF chain thing you are mentioning? Like for example, like in FR1 or FR2, like okay, before coming into RF chain, let's talk about fully digital precoding. So what do we mean by fully digital precoding, and why the name also?
Pre-coding is done in a digital domain.
Okay. Okay, pre-coding is done in digital domain. So let's talk about this particular step. If I try to draw a resource grid kind of architecture in time and frequency, and let's talk about this symbol here. Let's call it xk. So what is the precoder I'm going to use here? Assuming that uh, channel changes across each subcarrier. This is kth subcarrier, by the way, and I'm not considering the symbol notation for the easy. So is that the precoder? Let's say I'm going to use the precoder V, and I also mentioned now the channel changes across subcarrier. That is more familiar in scenario in FR1, because in FR1 you have a mixture of LOS and NLOS path, like line of sight and non line of sight path both, where we actually saw every kind of phenomena like reflection, scattering, diffraction, all this thing. So this precoder that I am going to use, is that going to be constant across the resource grid or not? If my channel changes across the subcarrier.
Yeah, for some a few groups of PRBs it is same, but as we change
Okay.
PRBs,
So
it
let's
might be different.
okay. So let's take this extreme case where the let's say uh, my channel changes across every subcarrier, not even a group of subcarriers. Like in practice, of course, it's over a group. Otherwise, the complexity is going to be huge. But let's, for sake of theory, let's assume the channel changes across each subcarrier. So the precoder I'm going to use should change with every
Yes,
subcarrier, or okay,
yes,
so
yes. Should change with your subcarrier.
VKXK.
Yes.
Fine. And we are calling it fully digital because we have mentioned already in the digital domain. And there is also another way to say, another way to see it, that we can both vary the amplitude and phase. So we can vary both the amplitude and phase of this precoder. That is also one of the options. So we have this resource grid, and then we have seen that we have to do this IFFT thing to create a sequence in time domain. So this precoding, when for fully digital precoding, when should I do? I should do after this IFFT step, like here or here, before the IFFT step. If I talk about the resource grid here, this is in time frequency domain. I perform IFFT. In what domain I am now?
Once you take IF, it is in time domain.
Then I am completely in time domain. So my question is, this precoding of these symbols, that is done after doing IFFT, like after coming into time domain, or it is done before IFFT, like in time frequency domain?
Before time domain.
No,
Before
you need to do it in the time frequency domain, because once we are in the time domain, the orthogonality is kind of lost. For example, when I say orthogonality, is it's like xk, that precoded xk thing, that symbol is spread across the subcarriers. So you cannot separate it. So first you need to precode it, make it vkxk, and then you perform the IFFT, and the rest follows. So good thing about fully digital pre-coding is that we can, as we mentioned, that we can both vary amplitude and the phase, and this is possible by how, by the way, like for example, if I have 64 antennas for fully digital pre-coding, is there only one such resource grid? That we have encountered already in last session, that when we have multiple antennas, so is there only one resource grid and then being transmitted, or how does it happen for fully digital pre-coding? Actually you need to have resource grid and this IFFT and then CP addition and whatnot for each of these antenna. So there are 64 such resource grid here for fully digital pre-coding. So you can see that complexity is pretty huge. So when you talk about this RF chain only comes into picture after you do IFFT here and then CP addition, and then comes the RF chain part. So what does it contain if we talk about at transmitter end? When we mention the name RF chain, is that a single block or there are multiple blocks involved and we call it RF chain together?
There are multiple blocks certainly.
Okay, so let's talk about at after IFFT and CP addition. Let's talk. We do the CP addition also. In which domain we are still?
Time domain,
Time domain. If we talk about analog or digital domain,
digital domain.
we are still digital domain, but we cannot transform the digital information, right? So that's where
Yeah,
we RF domain, RF chain comes into picture. So I need to pass them through
DSCs,
DSCs. Is one of them sufficient?
two DSCs
Two DSCs. And why so?
in phase and quadrature phase.
In phase and quadrature. Then
Then up converter and power amplifier.
up converter. So in terms of this cos 2 pi fc, I have sin 2 pi fc, and then
Power amplifier.
power amplifier,
Addition power amplifier.
and then we okay transmit. Fine. So this is kind of the most expensive and the bulky part when you talk about RF chain, both transmitter and receiver side. And also the name fully digital pre-coding comes into picture because we are digitizing the content of each antenna. That is more understandable if we talk about the receiver end. So if I talk about receiver end, you receive an antenna and then you pass it through band pass filter. Then comes your ADCs, low pass filter. So you can see and then of course this again this CP removal and FFT and bringing back the time frequency is kind of resource block demapping, and the rest of the thing follows. But the point I want to bring here is that the content or the signal you are receiving at each antenna is passing through an ADC DAC. So that way you are working on, you have the flexibility to work on the digital version of signal that is received across each antenna. So that is one good thing about fully digital precoding. You have lot of flexibilities, and flexibility means, in terms of, if we talk about math, you have the capability to vary both amplitude and phase. That is, you can vary the precoder across PRBs, across users actually also. If you like, it's up to your design. You can assign receiver orthogonal frequency. You can multiplex multiple user also to send them over the same PRB. Of course your precoder need to be a bit advanced for that, like ZF or MMSE, because you have multiple streams and you are trying to transmit them over the same PRBs. But all you can do because of this fully digital precoding, because when it comes to the maths part, it's because you have the flexibility to vary both the amplitude and the phase. So this is feasible in FR1. We have seen the multiple transmitter receiver design in FR1 in the course that is mentioned. For example, there can be like single user MIMO, where basically you assign the entire bandwidth for a user, and then what you do, you multiplex, like basically you bring in multiple layers and transmit them over same PRB. When it comes to multi-user MIMO, then again the similar idea only. You have one transport block, let's say for example only one transport block for each user, and you are multiplexing them over the same PRB and then transmitting using different precoder, of course, for each of the user and each of the PRBs. And this all you can do, because you have the capability to exploit or vary both the amplitude and phase. But then the computational complexity we have to keep in mind. For each antenna at transmitter side, you need two DACs, up converter and power amplifier, and at the receiver end again ADCs, band pass filter, round converter, and you will have resource grid corresponds to each of those antennas. Now my question is, you can tolerate this in FR1, where you have relatively less number of antennas, and also you are in badly need of transmitting multiple layers over the same bandwidth, over the same PRBs in the sense. So you can still afford that, okay, less number of antennas and all that. But what about when you move to FR2? So let me introduce a new slide here. The moment we move to FR2, this is not feasible. And can you point out why this fully digital precoding thing? Like basically what I'm
The
asking,
complexity only, because of complexity.
complexity increases hugely. Is there some any like other reason, like physical constant maybe? Like even if I am willing to bear the complexity, what are the consequences? Or okay, you mention the complexity thing. Fine, we'll have lot of complexity. Let's say I'm for some reason I am willing to bear that. That I'll okay, I'll have that. In that case, at the receiver end we have handhold devices, right? So having, let's say, 16 antennas mean 16 RF chains. Now we
Yeah.
have seen the spacing between antennas is lambda over 2, and when you talk about lambda over 2 spacing between antennas, so basically the spacing between antennas is in the millimeter range. So we won't be able to fit that many RF chain even. It's like it's a physical constant. Even if I am willing to bear the complexity, that many are simply not possible, because the distance between antennas are itself very less. but the RF chain size, that doesn't scale like that. That still remains same. So for FR2, what is the way out? But again, you mentioned earlier that FR2 I again need not transmit multiple streams, so that way I need not multiplex the, like multiple users or something, at least over the same PRB. So how does it happen? Let's talk about the simplest case of FR2 when I'm having a single user and a channel that doesn't change over frequency. So by the way, what kind of channel is that when I say that channel doesn't change over frequency? It's
It's simply fading channel. It's simply fading channel.
okay, so it's like a frequency flat channel, right?
Yeah, frequency flat channel.
If I try to have the
Yeah,
channels,
attenuation is going to happen.
okay. So if I try to draw the channel spectrum over the frequency band of what I like, what frequency band is of concern to me, it's basically constant. So there is no variation with frequency in the channel. So now I am trying to bring the same resource grid and try to see what change it makes compared to FR. Anyway, there are 14 symbols, but not I am drawing not all of them. So earlier we have, let's say, if talk about the symbol at this particular place, and we don't consider the symbol index just for simplicity. We have earlier VKXK. We mentioned that V also has the index K because precoder was changing because channel was changing. But FR2 I am assuming that I have a frequency flat channel. And by the way, any example of frequency flat channel, like maybe the simplest one, like what kind of channel doesn't really change over frequency? Line of sight channel, right? There are other possibilities, but that comes to our mind first because that doesn't really vary with the frequency. So this what is that? Oh, yeah, this VK thing was earlier varying with K, and K was the subcarrier index or the PRB. So now instead of VK, what I can write?
It's independent of K.
It's independent of K. So now I am transmitting this precoded symbol VXK. Now if I uh, do that IFFT thing and get my time domain sequence and try to write the math here, let's say the nth element here, let's call it xn, and let's say IFFT is n capital N point FFT. So and n is by the way number of subcarriers here, the capital N. So xn can be written as part of IFFTs as v x k, sorry, e to the power j 2 pi n k n, where k runs from 1 to n or 0 to n minus 1.
This is X tilde or Xn. Xn is simple Xk. Yeah, FFT of or IFFT of Xk.
Okay, yeah, I should change the notation, otherwise it's confusing.
Xn is simply IFFT of Xk. Actually. Yeah,
Okay,
correct.
so earlier let me just write here v index k. So earlier when I was mentioning the orthogonality is destroyed, like uh, in the way, let's say if the v is also dependent on k, so is there any way I can write it as some, let's say a times uh, FFT of the symbol here. In FR1 I am saying I was not able to write that, right?
Yeah. Yes.
And that is the reason you are mentioning that I need to do pre-coding here, not here. Because if I am able to write it as some a times the IFFT of plain symbols or unprecoded symbols, then I can just multiply a here also. I need not do it here in the precoding, but just because it was also varying with the index k here, that is the subcarrier index, I am forced to do the precoding here and then perform IFFT. But now in FR2 I don't have the constant, so it's V only. So now I can write it V times this. So what flexibility does that give me? Now am I still forced to do precoding here,
Hmm.
or I can do sometime later?
Yeah, you can do in RF domain. You can do after up conversion.
Okay, so basically you can do the precoding in time domain now. And the assumption behind that is,
In analog domain, time or analog domain. Everything is time domain, analog domain.
yes, so channel is a frequency flat. Fine. So I have this single user case. I am assigning the entire bandwidth for its requirement, and I am also using the precoding in analog domain. So that is good thing. So thing is that now I mentioned one point. I just reinforce it here. When I talked about fully digital precoding, I mentioned when it comes to math part, you can vary both the amplitude and phase of precoder. But this is what we call analog precoding here. So let us point it out, analog precoding. So analog precoding, the main constant in terms of maths part is that you can vary only the phase. So if V is a scalar here for a CISO system, single antenna case, it's some e to the power j theta, and of course if it's a vector of dimension n, you have e to the power j theta 1, e to the power j 2 theta, like that. So analog precoding, we don't have the flexibility of having this like we cannot play with the amplitude, we can only play with the phase part. So by the way, uh, so single user frequency flat channel, how many RF chain we need now to implement this V thing? Earlier we have seen in frequency in fully digital precoding, for each antenna we need one RF chain because we are precoding in the digital domain. But now we have the ability to precode in the time domain or analog domain, because my channel is frequency flat, so I can do it after IFFT. So do I still need 64 antennas here? Sorry, uh, do I need here 64 RF chains? Like, is there one resource grid is sufficient, or I need to again have 64 resource grid as in fully digital precoding?
One is sufficient.
One is sufficient. Okay. So let's say I have one RF chain, but this RF chain is still connected to multiple antennas, right? Because the number of antenna doesn't change. And you already mentioned that for FR2 we make use of the antenna to create a beam kind of structure. So do I directly connect the RF chain to these antennas like that, or there should be something in between to implement the recorder?
Use phase shifters.
You have to use phase shifters. So what is the benefit of using if I compare like phase shifter to ADC DAC or up converter, are phase shifters more bulky, expensive? Do they consume a lot of power, or how is that?
May not be.
Yeah, actually phase shifters are implemented in analog domain, so they are very like low complexity blocks.
But these are programmable phase shifters, right?
You are talking about the implementation part, whether like
Yeah.
any
Yes. 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 Are
okay.
they are they programmable phase shifters?
uh, I don't have like much idea in the current 5G test bed whether they are using the conventional analog ones, or they are just using the programmed version of that. So
Because for every direction we might require different phases. So we require needed to program these phase shifters to
ha ha
provide
ha,
appropriate
okay, true
phase.
true true.
Yeah. Yeah.
That need to be tuned, right? Correct, correct.
Yeah.
So my question is this: when this one RF chain is connected to 64 antennas through phase shifters, uh, what I can I okay can I create this kind of beams like these three beams in three different direction? Let's say this is at 0, this is at pi by 3, this is at minus pi by 3. Because if I can do this becomes great, because I can then theoretically serve UV1, UV2 and UV3 at three different location over the same bandwidth. So is that a plausible option if I use a single RF chain and 64 antennas connected via phase shifters?
There might be algorithms available to create it, but it is not required. So, for
Actually,
example, there is broad beam for massive MIMO system. There is an algorithm available to create a broad beam.
yes. No, actually, I'm not talking here. We are not talking about like broad beams. We are talking about three narrow beams in three different directions.
It really depends upon all these phase shifters how the beam is formed.
Okay. So the actual thing is, if we have only RF one RF chain, the issue is even with having the phase shifters, we can direct the beam in only one direction.
So it's not required to direct in three directions. Yeah, because it is meant for only one user.
Yes, true. So yeah, like what I'm trying to point out here is also it's not also possible. Like even if I want, let's say if I try to
Okay.
multiplex three
Yes.
user here, like just sum up their signal and try to transmit them in three different direction, it's not possible. So using phase
Yes.
shifter we
Yes.
can really create a very narrow beam at any particular direction that is sufficient to serve a like a long distance user, but multiple beams are not possible. That is only possible in fully digital, or to be really compare, to create three different beams I need three different RF chains. Then only I can create, because this architecture here, one RF chain can only create beam in one direction. It can be very narrow, but still it's only in one direction. So here again I have one more question, like since we are talking about single user uh, using up the whole bandwidth and line of sight channel. So how is there any way FR2 can serve multiple users, or it's not possible at all?
Use different symbols in a slot.
Okay, we have to use different symbols in a slot. Fine, but is not that going to make what is that data rate kind of slow, because I have to wait for the period of one symbol, then only I can move to serve another user
Yeah.
like that.
The slot duration is very short
Okay, so
because
if
carrier spacing is yeah around
okay,
120 kilohertz or two.
so if R2 you are saying that subcarrier spacing is around 120 kilohertz or 240, so that makes slot duration and thereby the symbol duration really small. So users can be served much faster compared to FR1. Okay, so I was just hoping we have a, let's say, uh, at base station end we have three antennas and user end also have three antennas. So my channel is a 3 cross 3 matrix, and we know that when base station transmit the CSI RX, user feedback the MCS. On top of that, user also feedback the something called rank indicator. So how does user compute for this particular case? Let's say it's a 3 cross 3 matrix. So let's say user have a code book for rank 1 precoder, some code book for rank 2 precoder, and another code book for rank 3 precoder. Let's say there are 4 rank 1 uh, precoder, code rank 2 there are 2, and rank 3 also there are 2 precoder. So if the channel is already 3 cross 3, so how exactly user um, compute the rank, like or to be honest, what should it like feedback, like which precoder to use? Because even if the channel is 3 cross 3, there is very good, like sometimes there is a chance the correlation between two antennas may be so high that the columns are kind of independent, so it's not a rank 3 matrix essentially, it may be a rank 2, or even in a worse condition it can be rank 1 also. So how user really proceed in that case, like what should it tell the base station that where to choose this precoder from?
There is a rank calculation algorithm.
Okay, so user should start from the rank 3 code book.
Rank 1.
Okay, so okay, it will start from the rank 1 code book, fine. So it will compute the corresponding SNR. This is rank 1 we are talking about, that means there is single stream, so it will have only one SNR value. And what is that called? Okay, let me write it down. Let's say R1 max rate, and then what user do next? Like, is that going to feedback the index, like the rank indicator, as 1, and also tell the base station to use the precoder which have the best SNR? or should it look into rank 2 and rank 3 matrices also?
Yeah, I should proceed for rank 2 as well and find out max rate there.
Okay, so there basically you have two stream. So whatever you have, like for each uh, precoder in the code book, you'll have this sum of SNR1 plus SNR2, and you will pick the max of that. Fine. And what about it should go up to rank 3?
Yeah, it might go up to rank 3 in this case. It's
Okay.
up to 3 by 3.
So basically it saves the R1 max rate, save the precoder index, or save R2 max rate, save the precoder index, and R3 max rate, and save the precoder index. So what next? Then how should it decide?
Then find out max and use that as a rank.
Okay, so it should compare
Find out
between
max of max. Yeah,
R1 max, R2 max, R3 max,
correct,
like that.
correct.
Okay. So let's talk about a hypothetical scenario when I found that the channel rank is actually 1, and it turns out that R2 max rate is greater than R1 max. What the user should do in that scenario?
So rank should be true now.
Okay, so let's is that even like possible? The channel
It's
being
not possible. It's not if rank is 1, R1 max is going to be higher.
and why is so? Like, what would be the problem with R2 max? Like, why cannot like R2 max be higher? So essentially, channel rank 1 means we can support only one stream, right?
Yes,
So when I
yes.
talk about 2 SNR, that means two streams. So the second stream will never reach the user. Like we
Mm,
cannot decode it at all. So there cannot be any
mm.
SNR2 kind of thing. So if the channel rank is 1, of course, you are, as you said, that R1 max should be greater than R2 max. So let us try to answer one or two model questions. So we are supposed to find the parameters that the user do not consider while reporting the rank indicator back to Gnode B. So does user consider number of antenna at user end?
Yeah, required. Yeah. Yes,
No,
not required. Why? Rank depends upon minimum, right? Minimum antenna that you and GNB.
Yes, true. But user is not going to consider that, right? Because ultimately user have the codebook available for different ranks, and it would compute the capacity for each rank level and then make the decision. So number of antenna at user end is not going to play a role there, right?
Okay.
So now does it really care about the number of antenna at base station while reporting the rank indicator?
No.
How about the MCS? Does MCS play any role in rank indicator RI reporting? It really doesn't care what modulation and coding scheme supposed to use when it comes to especially rank indicator. So both are actually wrong. So which parameter then user really consider when like reporting this rank indicator thing? Which is the sole concern?
Channel capacity.
Channel capacity is your sole concern. Based on that, you will take the decision based on the rank indicator. What about the statement that is true for FR1 MIMO system? It is said that users are not multiplexed in frequency domain. Is that right?
No, it's not right.
Not
No.
right. This is wrong. What about the second point? Should
That
I
is
use
also wrong.
should I
It is
use
wrong.
Not correct. Yeah.
what about the third one?
It's not correct.
Why is so?
So the orthogonality is present in frequency domain.
Okay. And what happens if you take IFFT?
It gets lost.
It is destroyed. Correct. That is also false. What about the fourth one?
That is correct. This is correct.
But when you talk about transmitter, we don't use ADCs, right?
Oh, oh, DSS. Yeah.
It should be DAC. So
Okay.
the fourth one is also wrong. So what about the factors affecting the system architecture between FR1 and FR2? Does is there any difference in terms of code block
First is
segmentation?
correct.
So these are same you are saying for FR1 and FR2. Okay. What about the second one?
They are different.
So number of antennas that you require are not going to be same. Okay. What about the third one?
They are different also.
Phase shifting is for analog
Yeah.
kind of precoding. And what about the fourth one?
Yeah, the same.
So if the code block segmentation, TBCRC calculation, all this upper layer of physical layer design are not affected for both FR1 and FR2. So it's about the precoding, whether it's being fully digital or analog or a combination of both to multiplex multiple user and number of antennas that makes the difference. Fine. So this is about synchronization signal. By the way, in what context synchronization signals are used? Like if we talk about synchronization signal, why they are required at the first place?
during initial access.
Initial access. So what is so special about initial access? Like, what are the things that happen in initial access only and not the later part of communication? Like, what I'm trying to see is the what is the speciality, like, initial access, what are the things that only happens, like, during the initial access only, like basically the uniqueness. And once something is established and that is followed throughout the rest of the communication, that is fine. So by the way, when you say initial access, you means, for example, when our mobile first time try to connect, enter a network, right? So when it tries
You
to,
identify slot boundaries.
okay, slot boundaries. And why is it necessary to find slot boundaries? And why they don't have any information about that?
To prevent interference.
Okay, prevent interference. But what I am asking that, why, like, why is not the slot boundary same for both base station and user? What is the issue?
Because of the delay, the round trip time.
The delay is present. Okay. Anything apart from delay that cause issue? Let's say I am removing delay out of picture. Let's say somehow, hypothetical scenario, I know the delay perfectly. That okay. Whatever the distance between user and base station, let's say signal travels in 5 nanosecond. So that is resolved. So is there any issue still at the initial access?
What about frequency offset?
Okay, let's say I have addressed that also via some uh, method. So is that fine, or something is still off? You know that delay exactly in terms of the distance between base station and user, and let's say your frequency offset is somewhat being resolved by some method. So is everything fine now, or there is still something off that needs to be taken care of? Okay, let's.
The time instant when the slot is starting, when the base station is starting the slot, the time at which the user equipment is turned on or enters in the network might be completely different.
Okay, so you're basically saying that timing reference or the clock that is used at both end, be at base station and user, they need not to be equal at all. Base station may have some T naught that is entirely different from, like, what user equipment I am using, or that is going to be different to some other user equipment also. Fine. So the notion of time is different between the user. So how is that going to create problem? Notion of time being different. Let's talk about a particular slot. Let's talk about the downlink transmission. So let's say base station transmit the data of the user in the fourth and fifth symbol of a slot, and if the timing reference of both base station and user are different, which is the common thing, which is bound to happen, so what will be the issue in that case?
All these channels PDSCH, PUSCH are defined with respect to slot and symbols in the slot. So
Okay, so basically you are saying if
everything will be
base
correct.
station transmit the downlink data in fourth and fifth symbol, the notion
Mhm.
of very fourth and fifth is completely different to the user. That's what you are referring to.
Correct. Correct.
So it
Yes. Yes.
doesn't know its starting point is wrong itself. So that is why that needs to be fixed. Okay, fine. Let's that is part of a downlink synchronization. So let's say that thing is adjusted. Is there some other kind of synchronization required? Something else apart from that? And downlink synchronization happens fine. For example, all users align the their timing reference with the base station, so they are basically at the same page. So there is no issue in the reception of downlink data. Is any other kind of synchronization required?
Yes. Uplink synchronization.
Uplink synchronization. So what is the issue in uplink now?
Yeah.
What
So
like what
what
is the
Dennis has
yeah,
what Dennis has talked, round trip delays are different for
round
different
trip delays
users.
are different. So you're saying users are going to be at different locations, so their round trip delays are different. Fine. And what happens really when our round trip delays are different?
Now there will be interference because of difference.
There will be
Now there will be
interference.
interference at base station.
There will be interference at the base station. Okay. So they have different round trip delay. So the whatever they are transmitting will appear at a different location. So the ideal scenario, what I am assuming, like in uplink, let's say user scheduled base station scheduled user 1 that you transmit at third slot, user 2 you transmit in 5 slot, and user 3 you transmit in 7 slot. So that whole things fall apart because user 3 may very well be close to base station, so it arrives early, and user 1 turns out to be the farthest, so it transmit in the third symbol only, but since it's the round trip delay is high, it arrives later. So everything is kind of jumbled up. So is that the scenario you are referring to?
Yes. Yes.
Okay. And then how it is being resolved?
By advanced transmission, by advancing the transmission with
By
that delay. Once it knows RTD, it can advance transmission.
okay, so let's by some existing method base station knows the this round trip delay, so it will inform the user to ensure something called timing advance. And so what is the concept of timing advance really? If I talk about if a user is far and if user is very close, so what is the concept of timing advance, how they should transmit?
So prior to start up, I mean this slot, like it can transmit. It can a
Okay,
slot and then a symbol number. It knows RTD. It can start transmission early.
okay, so the farthest one will start transmitting a bit early compared to the close one, so that when they appear at the base station, they appear at the position they should be.
Yes. Yes.
And then there is of course no interference in the sense because they are appearing in the same time, so there is no confusion. Then only I can do that rest of the processing like resource block mapping and all that. Okay, so this synchronization information and all that, how are they like scheduled? Is there some specific position or sequence, or what kind of information they carry really when you talk about synchronization signal or SSB? Let's say,
Yeah, transmit.
can you please repeat once? I'm not able to hear that.
I was saying they usually transmitted in a block, one block.
Okay, you will transmit one block, fine. And what exactly that block is going to contain?
It contains the PSS,
PSS.
uh,
Okay.
SSS, and PBB.
PBCH, right? Okay. So
Yeah, yeah, yeah.
when you say the PSS, the primary synchronization signal, what kind of sequence is that?
Length 127
Length 127
sequence.
sequence. And can there be multiple PSS per base station? Like for example, can one base station have multiple PSS or primary synchronization signal?
Kanak 3 additional.
True, there are three possible PSS, but what I'm saying, like, can uh, three PSS associated with a single base station? Because in that case, user is going to be confused, na? So actually, per base station there can only be one PSS, so that there is no ambiguity when during initial access. You should not have any ambiguity that which base station you are connecting to. And when you talk about SSS, that is secondary synchronization signal, is that also a 127 length sequence? So it is also a length 127 sequence, and but its number is much higher compared to PSS. It's 336. So that basically you can use in each sector and each cell. There are multiple use for that. Of course, we haven't talked about them. And what about this PBCH, or physical this broadcast channel? What information does it contain really? Long ago, we have talked about some common code set. So, does common code set transmitted in the SSB block or not? So, common code set is actually transmitted into PBCH. PBCH also contain multiple other information. For example, the system frame number, or that this, what is that, cell flag something. Basically, that denotes that cell is not working. So basically, you can connect to another base station. So let us try to answer this question here. So what are these statements true for the synchronization signal? Is the first one correct, that synchronization signal consists of PSS and PBCH only?
No, no, no.
So what is missing here?
The SSS is missing.
SSS is missing. What about the second one?
That is correct.
Correct. So by the way, it's mentioned that synchronization signal help user to find the slot boundary and symbol boundary. Okay, let us answer the question and we'll see. We'll talk about it later. What about the third one?
Second one is correct, no? Second one is correct.
Oh, sorry. Second one is correct. What about the third one? PBCH actually contain the system frame number. And what about the fourth one? Are synchronization signals user specific?
No, no, it's incorrect.
No, no.
So synchronization signals are not user specific, and basically base station doesn't know the channel of any user, at least who are trying to have the initial access. That is what it is intended for. So my question is there any property of the synchronization signals like PSS or SSS, like you are talking about 127 length sequence? Does there should any property like that it should satisfy, so that what I'm trying to see how the synchronization signal is going to help user to find the slot boundary. So basically the synchronization signals should have excellent autocorrelation property. Can one of you please point out why the autocorrelation property is so important aspect of synchronization signal, like how it's going to help? For example, let's talk about what user received. User received, let's say, synchronization signal. I'm denoting it as X and plus noise. By the way, X here is a sequence, and user also has a local copy of PSS. Let us call it X naught. So when I talk about autocorrelation, it should be Rx tau is equal to X n X naught n plus tau. N runs from 1 to capital N is the length of the sequence. Length of sequence. So why it should have a autocorrelation, excellent autocorrelation property, like, and how the autocorrelation property is going to help you find the slot boundary? Let's say user slot boundary is, let's say tau is 5 instant offset. So if I try to plot this autocorrelation here against tau, how the user is supposed to find the timing offset or the slot boundary? Basically, if we have the slot boundary, you can find the symbol boundary. So what do you think the autocorrelation is going to pick, where it should pick? Let's say user know what PSS is being transmitted and it has a tau is 5 offset. So if I plot the autocorrelation with respect to tau,
In the beginning.
can you just repeat once?
I said in the beginning it should be at the peak.
Okay, and the peak, where should it come?
Zero.
It cannot be at 0, right?
When tau is zero.
uh, but if it's 5 offset, that means whatever you have received, the noisy version should be 5 away compared to the local copy you have. it would be 0, it would be, the peak would be at 0, peak would be at tau is equal to 0 if your, there is no offset. Basically if your slot boundary and slot boundary at user and the base station are aligned, but they are not aligned, there is a offset of 5. So if your received signal is offset by 5 already, where should the peak appear?
Oh, at tau equals to 5.
Yep. So let's talk about, it should be something like this, and then here it would shoot up. So that's how user know that this is the offset compared to the slot boundary notion at the base station, and then onwards it will align itself. So by the way, for FR1, so we are talking about synchronization signal, physical PBCH, physical broadcast channel. So whenever we talk about broadcast, we are visualizing something like a beam of this sort. It's omnidirectional beam. That means power is being radiated at every direction equally. That happens when you have single antenna, and that fits into the FR1 framework. That's okay. But how about FR2? Because in FR2 you are forced to use multiple antennas, not because you need multiple layers, just because you need to achieve that antenna gain, antenna array gain to be precise, to increase your coverage. So but whenever you have multiple antennas, then you will run with the issue of having narrow beam. So how does the broadcasting thing happens in that case for synchronization signals? So in FR2 I have something, I expect in broadcast something of this sort, but in FR2 I am having something of this sort, maybe this or this. So how the purpose of broadcast is being served? Because the whole purpose of saying broadcasting means it should reach every corner of the cell. That means if let's say my user is somewhere here and you are sending your broadcast symbol here, is sorry, your synchronization signal is here, it doesn't make sense really, because then the user won't be able to access the network at all. So in FR2 we are forced to use multiple antennas. Now what should be my way out for transmission of this SSB, synchronization signal block?
You can steer the beam.
Okay, you can steer the beam, fine. So is there any specific name for that procedure you are saying? So you are saying at you are planning to do this also, this also, this also, right? So are you doing this all at the same instant? Because you cannot do that at a time, you can focus in only one direction. So how it should be done? You use something called beam sweeping. So at one instant here, at one instant focus your beam here. So in that way you cover the entire cell range by transmitting beam in different direction. That is the call, that is we call beam sweeping. So these synchronization signal blocks, are they transmitted at every slot? Because if I remember correctly, by the way, how many symbols does SSB occupy whenever it's transmitted in a slot?
Yeah, 4.
Okay, if I remember correctly, it occupies 7 symbols, right, in a slot?
No, no, 4 only.
4 only. Okay. So it occupies 4 symbol in a slot. Fine. And what about the periodicity? Is it transmitted at every slot? Because then it would be a huge wastage of resources. And initial access is not something that is so emergency.
So it is configurable. You can configure 5 millisecond, 20 millisecond.
Okay, okay. So let us see these statements here. We are supposed to find the false statement regarding PSS. So what about the first one? Is that false?
ASS we use time domain samples.
Okay. Uh, this one I'm also a bit confused because it's a length 127 sequence and it occupies 127 subcarriers. So isn't it supposed to be frequency domain samples?
But it is required for the slot boundary, right?
Yes.
So the slot will be in the time domain.
Okay. Okay, so it should be false. But still, I'll verify and update in the final.
Yeah, I'm also not sure. Like maybe check.
As of now, I'll mark it. Okay, so it should be false. So it should be the answer should be okay. So I'll just verify it once and update in the final version. So what about the second one?
I think this is
That is correct.
That is correct. So
The first one is false
okay, first one is false. Okay,
because this has to happen in time domain, not in frequency domain.
okay, okay. So I was got bit confused because PSS is a 127 length sequence that occupies this sub across the subcarrier. So I thought, yeah, but it should be in time domain samples only. True, that was my mistake. So what about the third one? Is that also false?
Third one is correct.
That is correct.
So it is not false. And what about the fourth one?
This is correct.
This is also correct. So it is not false. So which of the following statements are incorrect regarding initial access? is downlink synchronization. Of course, excuse me. You have seen. So it is correct only. Correct in the sense it is not incorrect. So does initial access any role regarding SRS based channel sounding?
No.
Neither do it have any role in the rank calculation, at least in initial access. And the same apply for MCS feedback. So next we have downlink synchronization, uplink synchronization, frequency offset, and the information that is in carried in PBCH like system frame number, common core set, cell flag. These are the information that is being conveyed in the initial access. So after completing synchronization using the SS signal, the user would have estimated which of the options are correct.
One and two.
Okay. So it doesn't have a role in PDCCH code set information. And what are the true statements for FR2? Is the first one true for FR2?
Second and third is
No.
true.
First one wrong. Second you mention. Second, should it be correct?
No.
Third also mentioned correct. What about the fourth one?
It's false.
So this is pretty much all about today's session. If there is any question, I'd be happy to take it.
I, I have a question to week 11.
Okay. So let me just open it.
So can I share my desktop?
Yeah, sure.
I hope it is visible.
I'm not able to see it yet. Others. Okay, yes. Now I can see it.
So this is the solution sheet for the assignment, week 11 assignment.
Okay.
Now for the question number 1, they are saying the answer is A and C. Okay. Because this is then periodic slot offset interval slots. Now what they have done is that while answering the questions, they are saying it is partially correct, although I marked A and C only.
Okay. But okay.
Now what they are saying that periodic 25 slots and slot offset 1, this is also invalid, although this is valid. You can see this one, this portion.
Okay, so correct answer they are saying
Actually, last week when the result came on the Wednesday, I got full marks on this question. Now they have reduced it. I don't know why. The answer sheet is also not in aligned with it because the answer sheet is saying that only A and C are correct.
okay. And they mentioned anything in the announcement section about updation of that or nothing? Like,
No, 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 no.
okay. So in answer sheet it's also A and C, and of course you have also marked
On
A
answer
and
sheet
C.
also it is A and C. On the correct answer are A and C only because you have to find the invalid. So
Yes.
this is properly valid.
Okay, I'll just ask the course TS once. Like,
Oh, okay.
I also seeing this kind of mistake for the first time. I mean, if answer sheet answer is it's matching, it should be a full
Mhm.
marks only.
Okay. I've stopped the sharing.
Sure, sure.
I think there is a question on the chat window from Dennis.
Yes, I am just answering for that. So SS signals are, you can say, cell specific when they are, according to my understanding, there is one base station per cell. But if there are multiple base station, then in that case it's more appropriate to say it's base station specific.
Saurabh, do you have any idea about the exam hall tickets when we'll get?
Uh, no, I don't.
I think most probably it will come by 15th. They are generally giving 10 days in prior notice on the in the announcement section.
Okay, okay, thank you.
So most likely we'll have another final session.
So I have a question in the chat box.
Hello, Dennis. Yeah. So you have like asked whether the SS signals are cell specific. So basically the answer is if you have one base station per cell, then you can say it's cell specific. Otherwise, it's base station specific. Basically, synchronization SSBs are all about initial access to, you're given access to a base station. So yeah, so it's like base station specific. But then again, if you have basically in general you have one base station per cell, so in that case it's cell specific also. Okay, different base station operating at different clock. Theoretically it can have, like, the idea is that base station have one notation of uh, like one timing reference, and whatever users are connected to it will align themselves. And if you change the cell, basically you are changing the base station, then if it's operating on a different timing reference, so I can see it's possible. Yes, a different base station can operate at different clock. When you say different clock, basically it's that timing reference we are talking about. That can be different. So if there are no more questions, I'll conclude this session. We'll have one last meeting, maybe on Tuesday. They'll announce it. I'll just try to come up with one or two model questions from each week, and we'll kind of discuss uh, just as a preparation for the exam. That's pretty much it.
So will it be next Saturday?
No, not next Saturday. I think it's a Tuesday. The
Tuesday, okay.
Tuesday is 14th, right? So yeah, it's 14th. 14th. Same timing, 3 to 5.
14, 3 to 5. Okay, same time.
Yeah, same timing. Okay. Thank you all for attending. Uh, I'm concluding this session.
Thank you. Thank you. Thank you.
Thank you.
Thank you.